Good evening from Cern, the European Organization for Nuclear Research in Geneva. My name is Paola Catapano, and right behind me you can see Cern's Globe of Science and Innovation, a wonderful wooden structure like a dome where Cern welcomes members of the general public to entertain them on subjects such as particle physics, but also the universe and futuristic technologies. Tonight the Globe is hosting the first of a series of presentations on the LHC, the world's largest and most powerful particle accelerator that Cern is getting ready for physicists worldwide. Follow me inside the Globe to know more about the LHC. The title of tonight's presentation is Tracking the Mysteries of the Universe with the LHC, and I have nearby me Michael Dozer, who is going to give tonight's presentation. Michael, thank you for accepting to answer a few questions just before starting this conference, which is actually in French and can be followed on a podcast entirely for the hour it's going to be, but in French. So let's try to just summarize in English through a few little questions, the main subjects of the highlights of the presentation. And the first question that comes obviously to my mind, and I think to anybody who doesn't know too much about physics, is why on earth building such a weird piece of machinery like the LHC underground here on the planet when you want to look after mysteries that are out there in the universe?
Well, there are two reasons. First of all, it's much cheaper to build here, and although the LHC is very expensive, it's in fact cheaper to build something like that here locally where you can actually bring in material. But the real reason is that the physics that you're looking at is physics that are very much at the beginning of the universe. If you look out into the universe with a telescope, you can see very far back in history towards the Big Bang. You can look back almost to 500 million years with the Hubble telescope after the Big Bang, where you still see galaxies, the first formation of galaxies. You can look further even than that if you look at the temperature distribution of the universe. If you look at the microwave background, you can see all the way back to 300,000 years after the Big Bang. But after that, the universe is opaque. You cannot see anything beyond that because light didn't make it out after that, earlier than that.
So that is 300,000
That's 300,000 years after the Big Bang. So if you want to see anything that happened earlier than that, well, either you have to detect gravitational waves or neutrinos from much earlier times, which is currently impossible. We don't know how to do that. These very, very weak signals.
They're still trying, though.
But these are much, much weaker signals than what people are trying to look for right now. So this is maybe a few centuries in the future in terms of what our technology will be able to do at that point. But if you really want to find out what's going on in the universe at the first instance, what you have to do is simulate it in a lab by colliding particles, which is basically what happened in the first instance of the universe.
So basically recreating a universe in miniature.
Recreating some aspects of the universe in the first few moments. Not a whole universe, it's a little bit less ambitious than that, but just what happened in the first few instances.
Okay, that's clear. And now, how come that this machine has to go at the speed of light, has to push particles at the speed of light, has to be 27 kilometers round, and has to have super ultra vacuum inside? What determines these characteristics that you've chosen?
Okay, so the one thing that determines the whole thing is really the fact that you have one equation, E equal mc squared, which says that if you want to produce something massive, you have to put lots of energy in it. If you have a collision between two particles, and they're moving very fast, you can generate this much energy by having them collide, by transforming their kinetic energy into the mass, but that means they have to have very high kinetic energy. Very high kinetic energy means moving very fast and using heavy projectiles. If you shoot two mosquitoes at each other, it's not the same thing as shooting two cannonballs at each other. So ideally you want something very heavy like a proton rather than something light like an electron, and you want to move it as fast as possible. So you can accelerate a particle by giving it a lot of push, electric push, but the important thing is that it has to go around an accelerator, otherwise you have to build a very large number of accelerating devices, which is very costly. So rather than building many, you build a few, but you keep using them again and again and again, which is what the LHC does. Any big accelerator does that. The problem that you have then is that these very heavy particles don't want to go on a curve. They want to go straight. So you need a very strong magnetic field to bend them, to keep them on track. And so ideally, you build a very big accelerator. The bigger the accelerator, at a certain magnetic field, the more energy you can put into the particles and still keep them inside the accelerator. And so basically the LHC has made the choice of using the highest possible magnetic field that you can build, which is about 8 Tesla, and using the biggest accelerating device that you can build, the biggest tunnel, which is the old LEP tunnel. And that sets the scale right away for the energy spread of the LHC, which luckily is in an area where the physics really gets interesting.
So you already had a tunnel that is 27 kilometers round. What if you had to build it from scratch? Would it still be 27 kilometers or even bigger?
It's basically a compromise between how much energy you want to put into the particles and how much money you want to spend. Making it any bigger, digging a bigger tunnel, would make it that much more expensive because you need the civil engineering and you need to use more magnets. You need to build more magnets. You need more electricity. You need more cooling. It gets very expensive very quickly.
Okay.
So in a way, the LHC is an ideal compromise between what was feasible and what one would like to have as a physicist.
Okay, we will know more about civil engineering in next presentation on the 7th of June, by the way. But coming back to the mysteries, people are flocking in the globe now. I can see them coming ready to listen to your mysteries. We'll talk about the mysteries after your presentation, but before going into what we don't know, what do we know today about the universe and how did we get to that?
Well, you have to look at the history of the last century, basically, of particle physics and of astronomy and cosmology. People have looked at atoms by scattering other atoms off them. They've discovered that atoms are basically a nucleus with a shell of electrons around them. They've looked inside the nucleus. They found that that's protons and neutrons. They looked inside that. They found that protons and neutrons have substructure, which is quarks. And they've discovered that all these particles that you can think of producing are, in fact, just made of a very small number, a simple set of 6 quarks and 6 leptons, and that the forces with which these particles interact are also a very small number. There are only 4 forces that exist in nature. So in a way, that's the outcome of 100 years of research in particle physics in 5 seconds. And the same development has taken place in cosmology and in astrophysics, where people have gone from looking at stars in our solar system, in our galaxy, to looking at other galaxies, to looking very far back into the past, to seeing superstructures of galaxies, and seeing the primordial radiation of the microwave, which is the temperature distribution of the universe when it was only 300,000 years old. And these two mesh very nicely together in a way that is somewhat surprising. It's very gratifying in a way that the two fit together and that we have a model that explains pretty much everything you can think of observing. So in a way, there's no mystery there. Now, where the mystery happens is that many of the things that our models explain rely on other things. For example, the fact that our quark model, our standard model of particle physics, predicts that all the particles are massless. We have no reason why they should have mass. So you have to come up with a good explanation.
But they do have mass in actual
Obviously,
reality.
yes. So the model is wrong somewhere. And we have to find out what's wrong with the model. We have to see if we can patch the model. And there is a patch called the Higgs particle, which people are very hopeful in finding. But there are other mysteries. For example, if you look at the universe, we only can see the stars of in the other galaxies. But if you really look at what's in the universe, you see that there's a whole amount of matter that you cannot see. It's just not bright. It's not shining. There's no light produced by it. It's dark matter. And there's about 6 times more of this dark matter than the matter that we have.
Incredible.
And even worse, there is something called dark energy, which permeates the whole universe, which makes the universe, the expansion of the universe, actually accelerate right now. So there's a lot of energy in the universe for which we have no good explanation, and that is about 3/4 of the total energy of the universe.
You still know it's there?
We know it's there. We've been able to see it. We've been measuring its effects, but we have no good explanation for it. So in a way, our whole model of the universe right now is just limited to those 4% that we can see, and the remaining 95% is our ignorance.
Maybe the LHC will help.
The LHC can help a little bit. For example, for the dark matter, the LHC is looking for something called supersymmetric particles, which could be one of the components of the dark matter that we do not see.
Or the mass, but we'll know more about it.
Or the mass, or maybe even extra dimensions. Who knows?
Yeah. Let's see. Have a nice conference, and I'll come back to you later.
Okay.
Thank you.
Si on résume la connaissance que nous avons actuellement, ça, ces 4%, c'est ce que nous voyons. C'est toutes les étoiles, toutes les galaxies, tout ce qui est visible dans l'univers. La matière sombre correspond à 5 fois plus de ce que nous connaissons que ce que nous voyons actuellement. Et là, nous ne savons pas ce que c'est. Nous ne le voyons pas. Nous ne pouvons que le voir indirectement par ces effets gravitationnels. Et je vais expliquer tout à l'heure que le LHC peut trouver peut-être un candidat pour cette matière sombre. Et là, c'est une catastrophe. 75% de l'univers sont inconnus. Et là, il n'y a même pas de candidat pour expliquer ce qu'il y a. Donc, le domaine d'application de notre modèle, dont nous sommes si fiers, qui explique tout, c'est ce petit bout de rien. Donc, un peu d'humilité. Alors, dans ce contexte-là, on peut se demander que peut apporter le LHC. Et ces trois domaines sont les domaines où le LHC devrait pouvoir apporter le plus. L'origine de la masse, expliquer pourquoi des particules ont de la masse. Et ça, c'est par interaction avec le champ de Higgs et donc la découverte de la particule de Higgs, que je vais expliquer juste après. Éventuellement, des particules supersymétriques qui pourraient expliquer ce qu'est la matière sombre. Et puis finalement, la possibilité de découvrir des dimensions supplémentaires à travers la théorie des cordes, ou qui sont prédites par la théorie des cordes.
And right after the conference, we're here with some of the members of the audience.
I'm a secretary in a bank in Geneva.
Okay. Did you know or did you suspect that what we know about our universe is only 4% of what exists?
No, I really had no idea about that. It was really interesting, but I didn't know.
And Jeremy, you work at Cern in the back-end sector, but only for a month. You just arrived.
Yes, I've just arrived and I'm doing a placement for my studies.
So you're finishing your studies?
Yes, but I also want to continue after that to learn more and to study more.
Yeah, and did you know about the Higgs boson? This phantomatic particle that they're looking for with the LHC.
I've heard some information about it, but really I didn't know what was this particle.
And now, are you curious to find about it?
Yes, a little more, of course, but it's still a little dark for me.
A little bit dark for you.
Yes.
Let's hope the LHC will clarify that very soon. And you asked a question before.
Right.
So, what is your background? Where are you from?
Well, I'm a software engineer.
Okay.
I'm working here in Geneva.
Okay.
And very enthusiastic about having the Cern so close to us, and of having such a big
Surely,
research center.
for people working in computing, the home of the web is definitely something
That's right.
fascinating.
That's right.
But were you also curious about mysteries of particle physics?
Right, I am in cosmology, but really as an amateur. So
What did you like most about the presentation today?
just making me feel what the LHC is for. So I had no idea. I knew it was for particle and detection and new experiments, but I didn't know which ones. And I think it was brilliantly explained
Today.
Yeah.
Thank you very much.
Thanks.
Last December, and he gave the LHC 5% chances to find a black hole.
He's
in
a
the
hopeless
collider.
optimist.
What's your bet for the Higgs boson?
Oh, for the Higgs boson, I'd be willing to bet my usual crate of champagne. If somebody will bet against the crate of champagne, another crate of champagne, at least even odds.
Okay, then we'll see in a few months.
Find somebody who will take the bet.
I take it.
Okay. So no Higgs.
At the LHC.
Okay.
Something
Very
else.
good. Very good.
We'll see in a few months' time.
Yeah, that's fine.
Thank you, Mike.
Okay.
Bye.